Okay, so we want to identify which of these graphs are continuous and then discuss those intervals where that continuity happens. Continuity is another one of those ideas we're kind of laying the groundwork for. You get a much more formal definition later. The problem is that you need limits. You need to have an idea of limits before we can formally talk about it, and we don't learn about that until the end of pre-calculus, beginning of calculus. So for our purposes here, we're really just interested in, can we draw this graph with one smooth motion without picking up our writing utensil? Okay, so for this, let's actually just look at our first graph. I'm going to zoom in a tiny bit so we can see it a little bit clearer. But in looking at this graph, can we draw this without picking up our pencil? Well, let's try. Wobbliness aside, right? But yeah, this can be drawn in one smooth motion, right? I guess you could mimic that motion with your finger. That would work the same. But this can be drawn in one smooth motion. We don't need to pick up our pencil or pen or whatever to do that. And so we would say that this is continuous on, and we would need to include its domain. And so again, because there are arrows on either end of this function, right? I would argue its domain is negative infinity to infinity, and we'll make that note. This is its domain. Okay, domain of function. So let's do the same thing for this next question. Okay, and again, our criteria here is, can we draw the whole graph without picking up our pencil or pen? And we always go from left to right when we're talking about domain values. So I would start over here in the bottom left, draw this graph, and now this part was fine, right? But in order to draw the whole entire graph, I have to pick up my pen and then jump up here to finish out the rest. So in this case, the answer is not completely continuous, right? Continuous. We can say the intervals where it is continuous though, right? So this is continuous on, and the only problem we have is right at this line right here. You should have talked about asymptotes briefly. We talk about them a little bit more later in this class. You should have touched on them in a previous algebra class. We're undefined when x is equal to 0, because then we would have a 0 in our denominator, right, which is undefined. So we're continuous everywhere except this x value right here. So it'd be from negative infinity to 0, union 0 to infinity. And this would be a sufficient answer to that question, right? It's just kind of saying where it is continuous, as opposed to this top part where you're just saying, no, it's not continuous. Okay, we have something similar happening here. So again, can we draw this whole thing in one motion? Well, if we start on the far left, that's the smallest part of x's domain, we have this first part, right? And then we have to pick up our writing utensil to draw this middle part. And then same problem, we have to pick up a writing utensil a third time, or a second time, I guess, for a third group, okay? So here, again, we're not continuous for the whole thing, but we can give the intervals where we are continuous. Continuous on, and we'll start from negative infinity, but then there's a pause. And on this graph, it's a little bit harder to just read what those values are. But if you notice, we did this on the last question, we looked at where are their domain problems, right? Where is our function undefined? That's what translates to these vertical asymptotes right here. And here. Again, straight lines tend to be an issue, but that's what we're looking at. So the way we get to that is by setting this denominator equal to 0 and solving. So let me actually scoot over a bit and we'll do that. So if we take x squared minus 5x minus 14 and set that equal to 0, this does factor. I see x minus 7, and x plus 2, which means this is x is equal to 7. That actually looks about right over here. And then, or x is negative 2, which seems about right for that other value that we have. So I would agree that this could be x is equal 7, and this could be x is equal to negative 2. So we're continuous from that negative infinity, that's going that direction, right? And again, this graph should have arrows on it. We'll blame whoever created it, up until negative 2, union from that negative 2 up until that value of 7, right? So from here to here, and we already went from negative infinity to there. Again, there's holes in each of those places, right? And then union, and we'll go from this 7 onward. All right, so that is where you're continuous. For this class, our goal is to kind of be able to look at it and visually have an idea of what's going on. Again, long term, you'll be able to solve for these a little bit more formally. Okay, last but not least, this one is all over the place, right? Which is fine. We've got piece number 1. I have to pick up my writing utensil. Number 2, and again, I have to pick it up, and 3. So again, we do have problems with our domain. Now, this one does not have vertical asymptotes defined, so it's a different scenario, but actually the result is pretty much the same. Do you see that we have this jump, this kind of spacing issue from this closed point down to that open point, right? So that actually is a place where we are not continuous. We had to jump down. And then very similar to that, we had to jump from this open point back up here to this closed point. Same problem, we're not continuous there either. So it doesn't have to be a full asymptote. We can do this where it's just a skip in the graph or a hole in the graph even. So in this case, we would say we're continuous on, and then again, we give those intervals. This would be negative 2, right, according to the point that's here, and then this would be 3 according to the point that's there. So this is from negative infinity until negative 2, union from negative 2 up until 3, union from 3 to infinity. And so a really good question might be, why is this a closed bracket, but we're putting an open parenthesis here? And it's because that's that disjointed part. That's the problem that we're having. It's from this point down to this point. There's a jump. So the function, it's kind of like a piecewise function, but there's like a disagreement at that exact value, right? It's defined up top. It's not defined down below. So overall, we do not get to include that value of 2. And for the same reasoning, 3 does not get included either. I hope that makes sense. So when it's one of those endpoints or kind of places where we jump from one value to another, we are not continuous there. Okay? All right. I will see you in the next example.